Okay, so yeah, my name is Alex Minnaar. I'm a research engineer here at Nitro, and my talk is an introduction to topic modeling and also some associated evaluation techniques. So just an outline, I'm first going to talk a little bit about what topic models are in general and what they're used for, and then I'm going to talk about how topic models are trained, and then how they can be trained in a scalable way. And then finally, how do we evaluate our trained topic model, and then a short demonstration of a Scala implementation. So what are topic models? Topic models refer to a collection of unsupervised learning algorithms that try to uncover the hidden latent structure within large document collections. So this hidden latent structure is encoded in what are known as topics. So at a high level, topics are clusters of semantically coherent words. So here's an example from our own Nitro corpus of documents. So this topic contains words like financial, capital, investment bank. So clearly these are all semantically coherent words, and you could say this is a topic about, say, finance or something. So the reason why these topics are so useful is because they're often human interpretable, like this one. So all you have to do is look at this topic, and you can know sort of the themes and ideas that are present in your large document collection without actually having to go through and read every document within it. So essentially, topic models create a low-dimensional representation of your document collection. So the most popular topic modeling algorithm is Latent Dirichlet Allocation, or LDA, so that's what I'm going to be talking about. So LDA was initially proposed in a paper in 2003 by David Bly, Andrew Ng, and Michael Jordan. So in LDA, topics are defined as distributions over words. So in this distribution, the high probability words should be human interpretable, so they should be like those finance-related words I mentioned earlier. And then the documents are defined as distributions over topics. So here's a good illustration of LDA. So on the left, you can see the corpus level topic distributions over words, and then for each document, you have a per document distribution over topics. This is called the topic proportions, and it's assumed that each word in the document is generated by first sampling a topic from the document's topic proportions, and then sampling that word from that topic, which is, again, a distribution over words. So what are topic models actually used for in practice? So they can be very helpful for searching and browsing and summarizing your document collection. So consider you have your document collection, you run LDA on it, you get your topics back. What you then can do is go back over your documents and infer the topic proportions within them, and then look at the high probability topics within those proportions, and then give your documents informative labels based on those topics. So then what you can do is you can browse your topics in an intelligent way. So think of the way Gmail sort of categorizes your email in their primary social and promotions tabs. You can do the same thing with your topics as tabs. You could also insert your documents and their corresponding topic labels into a searchable database like Elasticsearch, and then perform faceted search based on topic. So say you have a user that wants to search for a keyword, but only within, say, documents with a financial topic. So potentially the results would be much more relevant if you could facet by that topic. And it's also a powerful way to measure the similarity between two documents. So you can do this by comparing the topic proportions between each of those documents. And this is very useful because you can potentially have two documents that don't share any words in common, but if their words sort of belong to the same topic, then their topic proportions would still be similar, and you could discover that they're actually similar documents in that way. So there's lots of different applications. The list goes on. Excuse me. So an important question is how to actually train your topic models. So here's the graphical model for LDA. So so you have your observed words, W, which is the shaded node. So all of these nodes are random variables. And then you also have the per document topic proportions, which are theta. So there's assumed to be m documents in your corpus, and then you also have k topic distributions, which are parameterized by phi there. So when we say training a topic model, we mean we want to compute the posterior distribution of the per document topic proportions as well as the global topic distributions given your observed documents. So this is an intractable distribution, so you have to use approximation techniques like variational inference. So the way variational inference works is you have your intractable posterior distribution and you try to approximate it with a flexible distribution that you can sample from called the variational distribution. And this variational distribution has free parameters corresponding to your hidden variables, so your per document topic proportions and your global topic distributions. And basically, you optimize these by minimizing the KL divergence between the variational distribution and the posterior. And you end up with some update equations for each of these two variables, and they both depend on each other. So you can solve this with a EM-style coordinate ascendant algorithm, which is shown here. So basically, you start off with some randomly initialized topics. Then in the E step, you iterate through all the documents in your corpus, and you update the local per document topic proportions of each of the documents. And then in the M step, you update the global topic distributions based on those updates. And you basically iterate between the E step and the M step until you converge. So there's a problem here in terms of scalability. So you see in the E step, you have to iterate through all of the documents in your corpus before you can have a global topic update. So obviously, you need all of your documents in memory in order to do this. So if you have a very large collection of documents, this isn't possible. You can solve this problem by transforming this into an online learning problem. So this was done in a 2010 paper called Online Learning for Latent Dirichlet Allocation. So basically in the E step, instead of iterating over your entire corpus, you could actually just take sample a mini batch of documents from your full corpus and perform the E step on that. And then you get a set of intermediate topics, which you can then merge with your overall topics in the M step. So again, you iterate between the E step and the M step and sequentially sampling mini batches. So now you only need to have a mini batch of documents in main memory at any given time rather than the full corpus. So this sort of solves the memory issue. But still, if you have a very large document collection, that could mean a lot of mini batches to process, so it could be prohibitive in terms of time. So you can mitigate this by using distributed computing, like Spark, for instance. So you could distribute your mini batch of documents within an RDD and perform the E step on each document in the mini batch in parallel and then aggregate the results. So this way you can process larger mini batches, so you can get through a large document collection much faster than if you were to do it on a local machine. Right, so once you've learned your topic model, you want to know how to evaluate it. So this is an important question because the LDA algorithm has an input variable called k, which determines the number of topics that you will learn. So a common question is, how do you know what to set k to for your particular corpus? So if you can evaluate a topic model, then you could do a simple line search to find the optimal k value. So there's basically two different ways to do this. One way is using a statistical evaluation technique called perplexity. So what this is you initially divide your document collection into a training set and a test set. you train your topic model on your training set, and with those parameters that you learn, you can compute the predictive likelihood of the test set. So this is basically how like surprised your topic model is of these new documents. And basically, if the predictive likelihood is high, then this should correspond to a high quality model, and vice versa. So, however, there was a paper written in 2009 called Reading Tea Leaves, How Humans Interpret Topic Models. And in this paper, they carried out a large-scale human mechanical Turk, Amazon mechanical Turk experiment, where basically they showed people learn topics, and they asked them to sort of evaluate the human interpretability of those topics. And the results actually said that topics that were highly human interpretable were actually not correlated well with topics with high perplexity, and in some cases they were actually anti-correlated. So this sort of threw into doubt this evaluation technique. So then people began to use other evaluation techniques that tried to model human interpretability directly. So the idea is if you look at the high probability words of a learned topic, if they are semantically similar to one another, then that should mean that they are human interpretable. So in order to, yes? Sorry? The previous point. Well, yeah, I mean, I'll give examples later. So one way to evaluate sort of the semantic similarity between two words is to use word vectors. So I'm not going to get too deep into what word vectors are, but they can be learned via unsupervised neural network models. So these neural network models compute vector representations of words that seem to encode their semantic information. So there's a couple algorithms that do this, so word2vec and also Glove from Stanford. So basically, we know that these word vectors encode some sort of semantic information, because if you look at a word like France and its corresponding word vector, and then look at what words are similar to France in terms of their cosine similarity to their respective word vectors, you see words like Spain and Belgium and Netherlands and Italy. So clearly there's some sort of semantic information being encoded there. Right, so we use this, we can use this to sort of evaluate the coherence of the words within a topic, or the human interpretability. So basically the general formula is you take the high probability words within the topic, and then you compute the average pairwise cosine similarity between those words corresponding word vectors. So basically, topics with high coherence should be highly human interpretable. So for example, we did this on our own topics that we learned from our own Nitro corpus. So we ran a 100 topic LDA model on our Nitro corpus, and then we computed the word vector coherence of each of the learned topics. So on the left, you can see the top 5 topics by word vector coherence, and on the right, you can see the bottom 5 topics. So I think you'd agree that the topics on the left are much more human interpretable than those on the right. Right, so now I'm going to give a short demo. So in this demo, I'm going to learn a small topic model on a small sort of test corpus. So this corpus is 1,740 papers from the NIPS journal, which is a neuroscience and machine learning journal. So our learned topics should reflect this. So we're going to learn 20 topics from this corpus, and using online LDA, of course, and using a mini batch size of 30 documents. So, and then also once we've learned these topics, we're going to try to infer the topic proportions of a particular paper called Learning by State Recurrence Detection. And I'll just show you that paper. Well, I don't expect you to actually read this, but basically I chose this as an example because this paper sort of combines reinforcement learning and also neural networks. So the top proportions should reflect this, that it sort of has two high probability topics in its proportions. So I'll try to run this. Right. Bear with me. So it should be relatively fast, but just so we're not looking at it load, I have a pre-ran version here. So it's pretty. Yeah, can you see that? Okay. Right. So here, sorry, it's not that pretty, but here are the 20 topics learned. So as you can see, they're somewhat coherent. So this one corresponds to models and data and handwriting, like handwriting recognition, which is a machine learning problem. There's like speech signal auditory recognition, proteins, amino acids, which is like a neuroscience topic. But anyways, and here's also the topic proportions learned for the paper I showed you. And as you can see, the most likely topic for this document is topic 16 with 78%. So this is a topic that is sort of seems like it's about neural networks. And then the second most probable topic is topic 14, which has words corresponding to reinforcement learning, if you're familiar with that area. So yeah, that's my demo. Yeah, so it's pretty fast. Right, and I'm actually going to be open sourcing this implementation sometime in the future. So it's going to have implementations in Scala of online LDA and also online HDP, which is a non-parametric counterpart of LDA. And it should also have the option to run it locally or in Spark or in a purely streaming application with Spark streaming. And it should have the two word association measures for, the statistical and word association topic model evaluation measures. A smart vocabulary builder, APIs for topic proportion inference, some pre-trained models. So for example, if you don't want to train your own model for whatever reason, it can come with some pre-trained models, say on Wikipedia. So just general topics if you just want to infer the proportion of those topics in your documents, you can do that. And also a topic proportion-based document similarity calculator. All right, that's it. Thank you. Question?
So what does HTTP stand for and how is it non-parametric?
Right, so HTTP is a hierarchical Dirichlet process. So basically, like I said, a parameter in LDA is k, the number of topics learned. So in HTTP, it's assumed that there are sort of an infinite number of topics that could be present in your collection. So it's maybe not as useful as LDA, but it's sort of like a more flexible model. So some people think that it's better for, say, like a purely streaming application where you want to see how your topics sort of change over time. Yeah. Yep.
How would the resulting analysis be if you have a lot of, say, ties in topics?
Ties in topics? What do you mean tie?
So, like, let's just say, for example, your analysis comes back and you have a lot of different topics.
Mm-hmm.
They all have very similar frequency.
You mean like similar words within
Yes.
like duplicate topics? I mean, I mean, I've never experienced that, but I suppose that it would have a lot to do with your data set. Like LDA generally works better with larger data sets. I mean, I just showed a small data set for demo purposes, but I mean, that should be pretty unlikely to happen. I mean, unless there's a lot of sort of duplications within your data set that you're training.
Well, I guess the duplication could be avoided if you had some kind of sparsity constraint topics distribution. I don't know if there's any way to enforce that. So you enforce the topics different.
Right. So.
I mean, what prevents me from generating two identical topics and ascribing some arbitrary weights to them?
I'm not sure if I've never experienced that myself. I guess the model itself prevents that from happening.
There were a couple of topics over there. One of them had the word input and neuron, and yet another one, a different topic, had input and neural. And
Right.
so it did
Right.
seem like they were very similar. One was about neural networks, the computer idea. The other one was about neurobiology.
Right.
I'm wondering if you saw that phenomenon, two topics, that maybe one would be an analogy, the other or a metaphor.
Right. Well, I mean, this is sort of like a neuroscience data set that I'm running it on. So it's not that surprising that they would sort of be duplicates. I mean, they're not exact duplicates in terms of like the probabilities, yeah. I mean that tends to happen in LDA. Perhaps if you had a larger data set. I mean, this is a very small data set, so these topics aren't of great quality. But yeah, thanks.
Yes.
Yeah, go ahead.
I'm wondering, in terms of like, so your implementation of online LDA, Sparks 1.4 has online LDA too. What's the difference between them? And also, like, in terms of like the running EM, like Spark 1.2 actually has an EM implementation. Have you seen like the performance difference and like how is it different?
I mean, oh, okay. So how is sort of my implementation different from Spark's implementation? Well, I mean, I haven't done any benchmarking tests or anything like that. I mean, I'm sure both of our implementations are quite different. I haven't looked at it in a while, but I think Spark's implementation uses like GraphX and things like that. But yeah, I mean, once I open source it, I think I should do some benchmarking. That would be a good idea.
And how exactly are you planning on using that topic model in Nitro settings? I'm just curious because like there's like finding the number of topics, right? It's really hard. If you increase the number of topics, it's going to mix up the topics distribution you're getting, which is very bad. So I'm just curious on like how exactly are you planning on using or how
Right.
you're actually using right now.
Right. So, I mean, right. So how are we using topics here at Nitro? Right. Well, just sort of the other thing you said. I mean, so sort of whenever you run topic modeling algorithms like this, about 10% of them will be sort of incoherent topics or like duplicate topics or things like that. So that's sort of inevitable. But topics are independent with respect to each other. So once you're doing your topic proportion inference, which is sort of what's most important for us here at Nitro, you can actually sort of prune and pick and choose the topics that you want to use for the proportion inference. So you can sort of cheat that way. So to your point though, so we're using topic modeling here at Nitro, generally speaking, for things like smart search. So some of the examples I mentioned earlier. Yeah. Yeah.
One more question.
So it's more like a Spark question. When you run your mini batch and use the RDs, do you fit the partition as well, or to have performance optimization, or do you reshuffle your mini batch?
Sorry, please repeat the question because the mic is only for the...
Sorry, I was actually going to ask you to repeat the question. I didn't get
So
it.
when you said you run this implementation, you do the mini batch and you use like the partitioning of Spark and the RDs to run your if phase. Do you feed fix your partition, or do you reshuffle your mini batches every time?
So in practice, when I've done this, I haven't actually been literally sampling from the document collection. So what I've been doing is sort of creating a mini batch iterator. So sort of like an iterator of RDDs. So for example, if your documents were just in some directory on your system, you can create, and you knew the size of your mini batch, you can create sort of like an iterator through those text files and then parallelize them as RDDs. So I've never actually done it with pure sampling, as I said here. So.
On to the next talk.
Thank you.